I have to admit, I didn't understand a lot of your
Well, what I
comment.
talked about replaces the Newton's law of universal gravitation. We pointed out that mass is very much related to planet radius and that it can be highly correlated with the stuff that I'm talking about. But what we have observed is that the law of universal gravitation fails when you get up to huge scales like galaxies and multitudes of galaxies, as the astronomers tell us and the astrophysicists tell us, that they're off by a factor of about 20. That since the mass is only 1/20th, about 5%, according to Newton's law of gravitation. So when you're off by a factor of 20, you know you've got a problem with your theory.
Yeah.
Okay, the general research plan was to be able to calculate, independent of the distance of the Earth and other planets to the sun, both a centripetal and centrifugal forces where they would be in balance, and then predict what the distance of those planets from the sun is. That's the overall research plan. The distance from the sun is used as an input parameter in universal gravitation. Here, we're using other things as input parameters, and we're going to then see if this model that I have presented to you of two opposing forces when they're balanced, then we have a stable orbit radius. And notice all of this is a simplification because these orbits are not necessarily perfectly circular. So we're talking about sort of an average radius of the orbit and so forth. So there's a lot of complications in all of this. However, if we can get into the ballpark, we can actually tell you what the distance of the planets has to be according to the model of the law of motion and the momentum value in the centrifugal part of the balancing of forces of the radiation pressure.
Now, that radiation pressure, I haven't actually calculated here in the back of an envelope, but it's very, very small. It's certainly not a giganewton. I don't understand that. It seems to be out of all kilter.
If you want to use the Newton's universal gravitation, you're going to get different values. But we see that on large scale, according to the astrophysicists, Newton's gravitation is off by a factor of 20 when you get to the universe as a whole. And as long as the forces, regardless of their absolute size in terms of, I talk about a 1 billion newtons for the Earth. I'm going to calculate that for all of the planets in my spreadsheet there. As long as the centripetal and centrifugal forces are equal and opposite, that's all we need. Once we have those derived without reference to the capital R, which is the distance of the planet to the sun, we can then calculate the distance from the sun, which is an input parameter in Newton's universal gravitation. So which is more fundamental?
But I'm just concerned, Jim, about the magnitude of the radiation pressure. I mean, if you're sitting under a tree of standard height and an apple falls and hits you on the head, it hits you with a force of about 1 Newton. 1,000 million times that is the radiation pressure. That seems to be out of all kilter.
Well, the actual figures I got from an astrophysicist. And so it comes out to, about 1 billion newtons. And so it could be virtually any number, I suppose, but as long as it's equal and opposite to the centripetal or attractive force, you might say, between the planet and the sun, and the other planets too, by the way, because it's a complex system, we're good to go. We're off to the races. And we can look for a model of this that doesn't require mass, even though mass has been masquerading as the important input variable for quite a long time, and people have created dark matter all to try to cover up the missing mass problem in universal gravitation. You want to talk about the quantity of numbers, like an apple is, what do you say, 10 newtons or 1 Newton hitting your head from a tree?
I think it's about 1 Newton, yes.
Okay, it's about 1 Newton. If we just consider the ratio with dark matter to luminous matter, it's a factor of, about 1 to 8. So there you're 800% off. With Newton's law, the numbers tell us that it is not only wrong, it's like a route. it's like they're leaving the stadium with their heads bowed in shame.
It seems to be that you are attributing, if I'm not misunderstanding you, Jim, the centrifugal force to be a real physical force, whereas actually in the Newtonian theory, which I suppose you don't accept, it's a reaction. It's a fictitious force. It's one of these forces that arises like the Coriolis force and the Euler force when you have a non-inertial frame. For example, you have a rotating frame and you get these fictitious forces coming in. It's not a physical force.
I agree 100% with your description, Ian. And thank you, because that just strengthens my point that it's a fictitious force. So that actually Ian's argument is strengthening the rationale behind pursuing the research plan, which I proposed in today's talk. Because everything in that research plan is based upon measured values, and it aims to actually predict other measured values, which are, for example, the distance of the planet to the sun. If that is achieved, forget it. The binary mechanics model using the law of motion has completely decimated universal gravitation. I mean, forget it. Universal gravitation is wiped off the table completely. Everyone has been biased toward defending Newton's law of universal gravitation. It really is not fundamental in any way whatsoever. And because mass is correlated with planet radius, which is an important variable in what I presented, it tends to be correlated and hence to confuse people.
I kind of like the idea that there has to be an energy density difference in order for the bit to move out of its circular state, so to speak. You call it a bit cycle.
That requires clarification. Thank you, Harry. We can assume if there's no energy density gradient, we can assume
if there's not an energy density gradient, the bit cycle remains the same.
Yes, if there's not an energy density gradient, a particle can move one way or the other with equal probability, and so there's going to be no net motion of the object, okay? Now, we get the energy density gradient precisely from the radiation of the sun. With the side of the planet illuminated by the sun, it is going to have a higher energy density than the other side. And in actual data analysis I did of the moon using lunar laser ranging, other people's data now, okay, I found that when the surface of the moon is very bright, it has a higher temperature, it's emitting more quanta into the environment, and therefore it has a higher energy density in the direction of Earth compared to the other direction, which is the dark side of the moon away from Earth, and in the case of full moon. And in fact, I showed that the moon is about 10,000 kilometers closer to Earth during full moon than about 6 days or 7 days away from full moon. This was the first study way back in 2011, 15 years ago, where we were showing that objects tend to move toward volumes that have greater energy density.
Why should an object move in the direction of higher energy density rather than lower energy density? And when I saw that, my brain didn't like that.
The probability of motion is the same in both directions toward higher or lower energy density. In the case where a quantum moves to the higher energy density, particle formation is more likely. Whereas if a quantum move in the other direction toward a lower energy density, it's less likely to form a particle. Okay? So that given equal probabilities of moving toward higher or to lower energy density directions, what you're going to have is the net result is that particles are going to move toward the higher density area. And this is the logic of the law of motion. This is how it all was defined. And the nice thing about it in binary mechanics is that there's certain inescapable logic that you can't avoid. Once you quantify space-time and energy, certain things just occur. The sun creates a higher energy density on the surface of the planet, whether it's Earth the moon or any other object, than on the far side, away from the sun. And in fact, people have even published temperatures on the surface of full moon compared to the dark side of the moon, what the temperature would be there. We also have the Stepan-Boltzmann law, which relates temperature to watts per square meter, which is a version of energy density. All of these are basic laws of physics, which we are simply invoking, seeing if we get a better account of planet orbits, the planet distance from the sun, and on even larger scales in the universe of astronomical phenomena than the universal gravitation law, which has failed. You know, it's not like it's off 5% and people are worried about that. It's off by a factor of 800%, considering only dark matter, which is estimated to be about 45%. And then you have 5%, excuse me, that's 900%. That's a ratio of 900%. So that's like a whopping kick-ass loss. That's like a rout. That's not like, there's maybe a little detail in my theory that I need to adjust. That's like the whole thing, the whole edifice comes crashing down. And again, thanks to Harry and these cosmology sessions, I finally realized all this talk about the missing matter and that dark matter is at 45% is 9 times greater than the luminiferous matter. I mean, that's quite a route for universal gravitation. This might be the worst failure of a theory in the history of physics.
I'm not sure about that.
Well, you've got the 4 elements of the ancient Greeks, and that failed, and then they went to 5 elements. And now we're up to some 100 and some odd elements in the periodic table. That was a pretty colossal failure of the 4-element theory. But when you have universal gravitation off by 900%, you really have to just flush it down the toilet.